In this video, I'm going to discuss the solution for practice question 7.5. The question goes, the variables governing the resistance to flow, or also called the surface shear stress, denoted by tau naught, in a closed conduit are believed to include the flow mean velocity v, the conduit diameter d, the surface roughness k, the density ρ, and the dynamic viscosity mu of the fluid. In addition, if the surface of the conduit is itself in motion, then the surface velocity Vs may also be a factor. Okay, determine the dimensionless groups using the step-by-step method. So we have tau naught as the dependent variable, and it is a function of velocity, diameter, surface roughness k, the density, dynamic viscosity, and if in the case where the conduit itself is moving, then you have a velocity of the surface or of the wall of the conduit. Okay, now you should be familiar with all of these parameters except for maybe surface roughness. Okay, so surface roughness is a coefficient, and typically they do not have a dimension. So it's just a number. Okay, so how do we deal with a dimensionless parameter this early on? So we will do that. Okay, so the first step is of course to list down all the parameters. Okay, that's your step 1. So we have 1, 2, 3, 4, 5, 6, 7. So n equals to 7. Step 2, we are determining the number of primary dimensions available in this 7 parameters. So we list them down. So here we have tau. Tau is shear stress. So shear stress has the same dimensions as stress. And stress has the same dimension as pressure. So basically it's Pascal. So you should know that Pascal is newtons per square meter. Right, so that would be, you need to break it down. Newtons is kilograms meter per second squared, and then divided by area. So I'm going to just write it on the side here. So pressure equals to force over area. Okay, so the dimension for force is kilograms meter per second squared. So the dimensions are mass, length over time squared. We're dividing it by area, so 1 over L squared. Okay, don't take it for granted. Do it on the side or on another piece of paper so that you don't get it wrong. Okay, so this one can cancel. So we're left with m over LT squared. This is for shear stress. And then we have diameter, which is of course L, K, which is dimensionless, density, which is mass over length cube, viscosity is mass over LT, and we have Vs, which is length over time. Actually, I missed out something. I missed out the velocity of the flow. So that's a small v, also length over time. Okay, 7 parameters. Now the first step, we always get rid of length because we always have a diameter available in the problem. So get rid of length. So this will be tau naught times L. This will be gone. What about K? Okay, so K is already a dimensionless parameter. Okay, so once we've listed down everything, we can calculate how many primary dimensions we have. So we have mass, length, and time. Check that there are nothing else. Okay, so that's 3. Therefore, we move on to step 3. K equals to 7 minus 3. 4. So we are expecting pi 1, pi 2, pi 3, and pi 4. Okay, we are expecting 4 dimensionless variables in the end. So step 4 is we start to remove the dimension step by step. Okay, so the first dimension, now before we begin, we already have a dimensionless variable, which is this. K is already a dimensionless variable, so set this as one of your pi. This will no longer be part of our table. Okay, so now we need to find only 3 more pi's out of this 6 parameters that are left. Okay, so as usual, we observe and we remove length first. Okay, because we have a diameter here. So removing length. Now, tau naught is a shear stress and the unit is Pascal. We figured that out. So okay, so how to remove length from here? Just multiply tau naught times diameter. So you'll be left with mass over T square. Okay, and here is gone. This will be rho d cubed. Mass is left. This will be mu d mass over time. This will be Vs over d, 1 over t. Here you have V over d. Dimension is also 1 over t. Okay, next we get rid of mass. We use rho d cubed. Okay, so just divide tau d by rho d cubed. You will have tau over rho d squared. This will be 1 over t. This is already gone. This will be gone. Here we have mu d divided by rho d cubed. So that would be mu over rho d squared. The dimension is 1 over time. This one has no mass in it, so we just write them down again. 1 over t, 1 over t. So finally we get rid of time. Okay, so which one do we use? Alright, do we use, of course we can't use the first one, so do we use mu over rho d squared? We use Vs over d or V over d. So let's look again at what Vs and V are. Okay, so V is the flow mean velocity. Okay, and if the conduit is in motion, we have a surface velocity. Determine the dimensionless group. Okay, so which one do we use? Do we choose between Vs and V? Okay, so normally normally when you have two velocities like this, you will analyze and determine which velocity is typically the constant and which velocity is dependent on the other velocity. So in this case, the small v is the velocity of the flow. Okay, so we have a conduit here, we have flow moving through, and this flow will have a mean velocity v, and Vs is the velocity of the surface if in case it also moves. It could move in this direction, it could move in the opposite direction. So Vs is hardly the a function of the flow velocity, but instead is the other way around. The flow will be affected by the surface velocity. Okay, so from this we choose Vs. Okay, so coming back to our table, choosing Vs meaning you choose Vs over d, okay, because this is the parameter now. So manipulate it, just inverse this parameter to make it work here. So that will be tau naught over rho d times Vs. This is dimensionless, and this will be mu over rho d squared times d over Vs. So that would be mu over rho d Vs, dimensionless. Here it will cancel itself, and this will be V over d times d over Vs. So you will have V over Vs, dimensionless. So we are expecting some function of the velocity ratios, okay, because they are related. Okay, so now you have your pi 1, 2, 3, and 4. This is of course your pi 1. We have pi 2 here, pi 3, and pi 4. Okay, so as usual, write down the relationship function of pi 2, pi 3, pi 4. Okay, so I want you to expand it in your answer. So of course we identify Reynolds number. Okay, so I've said that it's okay if you don't recognize the other parameters, but I want you to identify Reynolds number. So here we have 1 over Reynolds. Again, Reynolds is rho Vd over mu. Okay, so that's it for this question.